let's jump right in. Today, we're cracking open Chapter 4 of the Eco Egypt training program. Looking at the requests, I realized we really need a detailed session about the TR station in Chapter 4. So today is all about the RMU, the TR, the MDB, and connecting loops to the MV switchgear. Basically, diving into all the details right from my book and slides. If you're out there working on utility-scale PV plants, this station is absolutely critical. It's the literal boundary where your low-voltage distribution network shakes hands with your medium-voltage system. Okay, here's our roadmap for today. We're going to hit the power transformer station first, then look at the LV main distribution board, the power transformer itself, the medium-voltage ring main unit, how we connect the MV loop, and finally run through some real-world operation and fault scenarios.
All right, starting off with Section 1, the power transformer station.
So what is this station really? Well, it's the critical interface between the medium voltage distribution network and the low voltage system. It's definitely not just a passive pass-through for electricity. It's the absolute backbone of your plant's safety and reliability. It takes all that power generated by your solar field, steps it up, and safely directs it right toward the main grid. This cheat sheet beautifully illustrates the three vital subsystems we're dealing with here. You've got this triad, right? The LV main distribution board handles the 0.8 kilovolts input. The 9,000 kVA power transformer sits in the middle, acting as the bridge. And the RMU manages that 33 kilovolt medium voltage side. Every single thing we're looking at today revolves around how these three pieces talk to each other. Moving right along to Section 2, the LV main distribution board. Let's look at the low voltage side first. Think of the LVMDB as the primary gatherer of energy from your solar inverters. When you're pulling power from a whole block of PV inverters at 0.8 kilovolts AC, you need some serious muscle. So it uses two massive 4,000 amp air circuit breaker main incomers to handle that load. Plus, it can take a 50 kiloamp short circuit hit for a full second. It's housed in an IP54 indoor enclosure to keep out dust and moisture and uses a TNS solidly earthed system. But honestly, the coolest part? The integrated digital SCADA metering. It turns this heavy-duty collector into a smart device, feeding vital stats directly to the plant's central nervous system. Okay, Section 3, the power transformer. Now we step up the voltage. This right here is the true muscle of the station, the 9,000 kVA power transformer. It takes that 0.8 kilovolt input and steps it way up to 33 kilovolts. And the engineering here is just brilliant. It uses a di-11 vector group, which gives us a 30-degree phase shift and actually traps and blocks the third harmonic from ever reaching the grid. It's got an ONAN cooling system that's oil natural, air natural, with a 6% impedance and an offload tap changer. On the safety side, it's heavily guarded. You've got a Buchholz relay, an oil temperature indicator that'll trip at 105 degrees Celsius, and a winding temperature indicator that trips at 125 degrees. Oh, and a quick practical tip. Keep an eye on the silica gel breather. If it's blue or orange, you're good. If it turns pink, yeah, moisture got in and you need to replace it immediately. Let's jump to Section 4, the medium voltage ring main unit. Heading up to the 33 kilovolt side, we meet the RMU. I like to call this the director and protector of the station. It's a super compact SF6 gas-insulated piece of switchgear. That SF6 gas lets it stay physically small while still safely handling 33 kilovolts and a 630 amp continuous current. It's tough too, with a 25 kiloamp short circuit withstand for 3 seconds. The gas compartment is totally sealed off at an IP65 rating, while the control section is IP54. And depending on your plant size, you'll usually see these set up as either a 2+1, meaning 2 load break switches and 1 vacuum circuit breaker, or a 3+1 configuration. Now there's a really crucial distinction here between the load break switch, or LBS, and a medium voltage circuit breaker, or MCVB. Think of the LBS as a traffic cop. It makes or breaks normal load current only, uses SF6 for arc quenching, and it doesn't have a protection relay. The MCVB, on the other hand, that's your emergency brake. It interrupts fault and load currents using a specialized vacuum bottle designed for huge 25 kiloamp fault interruptions. And it actually has an integrated numerical protection relay. So the LBS handles daily traffic, while the MCVB stops the catastrophic crashes. Section 5, connecting the MV loop. Okay, we've got the anatomy down. Let's look at the physiology, how the energy actually flows. It's a pretty seamless 6-step journey. First, your solar modules generate the power. Second, the string inverters convert that DC to AC. Third, our LV MDB gathers that power at 0.8 kilovolts. Fourth, the power transformer steps it up to 33 kilovolts. Fifth, the RMU directs that power through the medium voltage loop. And finally, step 6, that MV switchgear buses the power straight out to the utility grid. It's literally a step-by-step handoff from the desert sun all the way to the national grid.
And finally, Section 6, Operation and Fault Scenarios.
So, what happens when things go wrong? Well, let's start with normal operations to get a baseline. Everything is humming along. Both LBS1 and LBS2 are closed, meaning your loop is energized. The transformer VCB is closed and supplying power nicely to the LV-MDB. All your protection relays are armed, just quietly waiting in the background, and your SCADA system is actively monitoring everything. This is what we like to see.
But then, boom, a fault occurs on the transformer feeder. Instantly, the current transformers detect an abnormal current spike. They signal the protection relays, specifically the ANSI 50, 51, or 51G relays. The relay fires a trip command, the VCB opens, and the 86 latch activates, permanently locking that breaker open so it can't accidentally reclose. Meanwhile, the loop feed routes power to other stations, and SCADA immediately flags the exact faulted RMU for the control room.
So now we have to isolate and maintain it. Safety is the absolute top priority here. The VCB is open and physically racked out, the earth switch is closed, and this is huge. Mechanical interlocks engage. These physically prevent anyone from making a dangerous switching mistake like closing an LBS while the earth switch is on. Then, personnel apply portable earthing before ever touching the transformer. All right, maintenance clears the fault, time to re-energize. But here's the catch for step 2, that 86 latch relay. You can't just clear that from a computer screen. It has to be manually reset by a human standing right at the panel. Once that's done, the VCB is closed under strict SCADA supervision. The adjacent LBS units are reclosed and the system is back to normal.